Hello, and welcome to this lesson on ionic bonding. In today's lesson, we will firstly explain the concept of ionic bonding and understand its significance in the formation of giant lattice structures of ionic compounds. Then we will move on to gain a deeper understanding of the strong electrostatic forces that hold these compounds together. You already understand that ionic bonding involves the transfer of electrons between atoms, resulting in the formation of positively and negatively charged ions. Building on this foundation, today's lesson will advance our chemical understanding by showing you how ionic bonds lead to the formation of giant lattice structures. This will help us appreciate the significant role that strong electrostatic forces play in holding ionic compounds together, which explains many of their properties, such as high melting and boiling points. This deeper insight will allow us to see the connection between atomic interactions and the macroscopic properties of ionic compounds. Let's delve into the concept of ionic bonding and understand its significance in forming giant lattice structures of ionic compounds. An ionic lattice is a three-dimensional structure composed of alternating cations, positively charged ions, and anions, negatively charged ions. The ions are arranged in a regular repeating pattern, which is highly organized. Although individual ions are tiny, this repeating three-dimensional arrangement extends throughout the entire crystal. Imagine a piece of salt, which is sodium chloride. This salt crystal is made up of a regular arrangement of sodium ions and chloride ions stacked in a repeating pattern. We can represent this using a 3D space-filling mode. In this model, the spheres representing the ions are scaled to their actual sizes so that they fill up the space they occupy in the lattice. This provides a realistic view of how closely packed the ions are in the crystal. The ions in an ionic compound are held together by strong electrostatic forces of attraction between oppositely charged ions. This is what we call the ionic bond. The positive and negative ions attract each other, resulting in the formation of the ionic bond. These forces act in all directions within the lattice structure, creating a strong bond between the ions. For instance, in sodium chloride, each sodium ion is surrounded by 6 chloride ions, and each chloride ion is surrounded by 6 sodium ions. This goes on and on to form a giant ionic lattice. There are so many atoms that we would never be able to show the full diagram, only sections of it like this. This arrangement maximizes the electrostatic attraction and results in a very stable structure. We can represent this using a ball and stick model. In this model, spheres represent ions, and sticks represent the ionic bonds between them. For sodium chloride, you would use 2 different colors to represent the sodium and chloride ions. Then, you'd start by drawing one type of ion, for example chlorine, and forming lines from this ion to all neighboring ions. Ensure that all lines join opposite charge ions, in this case Na+ to Cl-. You would then extend this model for each of the sodium ions. This model is great for seeing the geometric arrangement and understanding the spatial relationships in the lattice. However, while it is a useful visual tool, it has its limitations. Unlike the 3D space-filling model, the ball and stick model doesn't accurately depict the sizes of ions and the distances between them. In the diagram, we see a relatively large distance between the ions, but in reality, there's very little space between ions. Another limitation is that it depicts the ionic bonds as rigid sticks, but in reality, they are electrostatic forces of attraction extending in all directions. By grasping the concept of ionic bonding and the formation of giant lattice structures, we gain a deeper understanding of the strong electrostatic forces that hold these compounds together, leading to many of their characteristic properties. This connection between atomic interactions and macroscopic properties is fundamental in explaining why ionic compounds behave the way they do. In today's lesson, we delved into the concept of ionic bonding and its pivotal role in forming giant lattice structures of ionic compounds. We discussed how ionic compounds consist of a 3-dimensional lattice of cations and anions, held together by strong electrostatic forces of attraction known as ionic bonds. These forces act in all directions, creating a sturdy and stable structure. By connecting atomic interactions to macroscopic properties, We gained a deeper understanding of why ionic compounds behave the way they do. This lesson has provided a solid foundation for understanding the formation and properties of ionic compounds, paving the way for more advanced studies in chemistry.